Today we discuss about the induced dipole moment in a molecule. We have seen the induced dipole moment in an atom. Okay, dipole moment developed in an atom when it is placed in an electric field. That was discussed in the last class. And for such an atom, we have seen the dipole moment induced. P is equal to alpha E. Okay, the field, electric field E, when an atom is placed in the electric field, the dipole moment induced in the atom, that is alpha E, where alpha is the atomic polarizability. So this we have seen, the mechanism behind the development of dipole moment in an atom that was discussed. Now we are considering a molecule. Okay, we are considering polarization of molecules. For molecules, the situation is not quite so simple as in the case of an atom, because the polarization is different. Polarization is different in a different direction. Okay, so the polarization developed in the atom or in the molecule, that is different in different direction. For example, suppose we have a carbon dioxide molecule. This is a carbon dioxide molecule. Okay, so here you might be applying the field along the axis or perpendicular to the axis. Along the axis means this direction. Perpendicular to the axis means you are applying the field in this direction, or you might be applying the field in some other direction. Okay, so depending upon the direction, the polarization will be different. If you are applying the field along the axis of the molecule, the polarizability, the alpha, is found to be 4.5 into 10 raised to minus 40 Coulomb square meter per Newton. Okay. Now when the field is applied perpendicular to the axis, the polarizability is found to be 2 into 10 raised to minus 40 Coulomb square meter per Newton. So it is different. It depends on the direction of the field. Okay. Now if the field is applied at some angle to the axis, suppose we are applying the field at some angle to the axis, then we must resolve it. We must resolve it into the parallel and perpendicular components. Okay. So the simple equation P equal to alpha E in an atom, that changes into this. P equal to alpha perpendicular, polarizability in the perpendicular direction, the perpendicular component of the electric field, alpha parallel, the parallel component of the polarizability and the electric field in the along the axis. Okay, so this will be the dipole moment developed. And in this case, the induced dipole moment may not even be in the same direction as that of the electric field. The induced dipole moment may not even be in the same direction as that of the electric field. It depends upon the value of alpha perpendicular and alpha parallel. Okay. So for a completely asymmetrical molecule, okay, the molecule may not be symmetric as the carbon dioxide. There can be a symmetrical molecule. The equation P equal to alpha E that is generalized or replaced by px equal to alpha x x ex, alpha x y ey, alpha x z dz, py equal to alpha y x ex, alpha y y ey, alpha y z dz, pz equal to alpha z x ex, alpha z y ey, alpha z z ez. Okay. So the three components, we know the dipole moment is a vector. The three components px, py, pz are given by this. Ex, Ey, Ez, we know these are the components of the electric field in x, y, z direction. Okay. So in this case, the alpha, the polarizability, that is a tensor. Okay, alpha ij, the alpha ij consisting of 9 components. Okay, 9 components, alpha x, y, y. These 9 components, it forms a tensor. Okay, this is called a tensor. So polarizability tensor alpha ij that constitute the polarizability tensor for the molecule. Okay, so generally the equation P equal to alpha E, that is written in this form, is alpha, that is a tensor. Okay. So in the next section we see the alignment of polar molecules. Okay, we are considering the alignment of polar molecules in an electric field. What we mean here is some molecules have built-in permanent dipole moments. Okay, they have built-in permanent dipole moments. Permanent dipole moment. Okay. Many molecules, for example, if you take the water molecule, oxygen in the middle, hydrogen, 2 hydrogens at some angle, at an angle of 105 degree. Okay, the angle between the bonds OH, that is 105 degree. So this molecule or the water molecule that has got a permanent dipole moment, because oxygen, as you see here, that is electronegative and it draws or attracts the electrons towards it from the hydrogen. From this hydrogen also it attracts the electron. So the oxygen becomes negative and the hydrogen becomes positive because they lose electrons. So a dipole moment will be developed. So even without applying the electric field, or even when the field is absent, the molecule, the water molecule in this case, this has got a permanent dipole moment. Because negative charge here, a positive charge here, that will constitute a dipole moment. The dipole moment of water is large. It is is 6.1 into 10 raised to minus 30 coulomb meter. This is not centimeter, it is coulomb meter. Okay, so a water molecule has a permanent dipole moment, and this permanent dipole moment of the water molecule is responsible for many properties exhibited by water. Okay, now what happens when a polar molecule is placed in an electric field? Suppose I place a polar molecule in an electric field. See, it has got a dipole moment, so kind of positive charge here, a negative charge here. You know what is a dipole? Dipole actually consists of a positive charge and a negative charge separated by a distance d. Okay, So we have a positive charge, negative charge separated by distance, and the positive charge will be experiencing a force F plus in the direction of the field. Okay, we are applying an electric field. So it will be experiencing a force F plus, and the negative charge will be experiencing a force F minus. Okay, so this is F plus is QE. A charge Q placed in an electric field experience force QE. And this one is minus QE. Okay, minus QE. Now, if the field is uniform, okay, field uniform, everywhere the field is same. Force on the positive end is QE, and force on the negative end is minus QE. And so the net force is equal to 0. So the net force acting on the dipole is 0. So what about the torque? Torque is N equal to R cross F, R cross F. So here the torque due to the force on the positive charge F plus is given by R plus cross F plus, and force on the negative charge is F minus, and the torque is R minus F minus. So R plus is D by 2, this is QE, and R minus is minus D by 2, and it is minus QE. So when you add, you will get Q into D cross E. Okay, Q into D cross E. You know why we are taking R plus as D by 2? Because distance from minus Q to plus Q is D. Okay, so this distance is D by 2, and this distance is minus D by 2. Okay, with respect to this origin. So we have this expression here for R plus. I'm taking D by 2, or R minus minus D by 2, and when they combine, you will have Q D cross E. And QD is the dipole moment. So N is equal to P cross E. So this is the torque acting on the dipole when it is placed in an electric field. P cross E. Okay. Now suppose the field is non-uniform. So the field that we apply here, that is non-uniform. So there will be one field, or one value of the field will be one value here, another value here. Okay, so in that case the net force is not equal to 0. Okay, so E plus is the field acting at the positive end, E minus is the field acting at the negative end. So force is equal to F plus F minus, that is equal to QE plus my Q E minus, and that is Q delta I. And you know what is delta I? That is the difference between the field at the plus and the, okay, that is the, and we can write delta X by using the calculus delta X. That can be written as the gradient of Ex dot D. Okay, because the field, this is the positive end and this is the negative end. Here the field is changing. Okay, so this can be written as delta Ex as delta Ex dot D, delta Ey, that is delta Ey dot D, delta Ez equal to delta Ez dot D. So delta Ex is the change in the electric field in X direction for a distance D, or for this D. Delta Ey, the corresponding change in electric field, corresponding change in electric field in Z direction. So delta E, when we combine these all, okay, we are combining these all. So when we combine, you will get this delta E equal to D dot del E. Okay, D dot del E. You know what is del? Okay, so that is written here. Now F is equal to F. This is the net force. Net force F is equal to Q delta E that we know. So F is equal to QD dot del E, and this QD is P, the dipole moment. Okay, so F is equal to P dot del E. Okay, in polarization, what happens? So when a piece of dielectric material is placed in an electric field, okay, what happens when a piece of dielectric material is placed in an electric field? If the substance consists of neutral atoms, okay, if this substance consists of neutral atoms, they will be polarized. Okay, they will be polarized because the field will induce in each atom a tiny dipole moment pointing in the same direction as that of the field. Okay, if the material is made up of more polar molecule, what happens is each permanent dipole will experience a torque that tends to line up it along the field direction. Okay, we have seen a dipole when it is placed in electric field, it experiences a force, the positive end experiences a force in the direction of the field, negative end experiences a force in the opposite direction. So this will be actually rotating the dipole in this fashion in the direction of the field. So if the material is made up of polar molecules, each permanent dipole will experience a torque tending to line up it along the field direction. Okay. So these two mechanisms produce the same result. A lot of little dipoles pointing along the direction of the field. That means the material becomes polarized. Okay. So if a material is not polarized, if the atoms are neutral, what will happen? The field will induce a dipole in the direction of the field. Okay, that is one case. Another case, if the atoms of the substance have a permanent dipole moment, when you apply the field will rotate due to the torque acting on the dipole. The field will rotate the dipole in the direction of the field. Okay, so these two mechanisms produce the same result, a lot of dipoles pointing along the direction of the field, and the material becomes polarized. Okay, and the polarization, we define a quantity polarization, that is P. This is actually capital P. We used small p for dipole moment. This is big P. This is polarization, that is dipole moment per unit volume. This is the polarization. So if you place a dielectric material in an electric field, okay, that will polarize the material. The dipoles will be pointing in the direction of the field. Okay.